Today we have Max Krasnow with us. He's a postdoc at the Center for Evolutionary Psychology at Santa Barbara. Max and I were more or less in the same cohort of people in the Center for EPSych, and he works with Lita Cosmides and John Tooby. They're on your committee, and he's studied things in a number of areas: social exchange and cooperation, which this is a part of, foraging adaptations, conceptual knowledge, social working memory, development of tool reasoning, and politics and coalitional psychology. But today we'll hear on evolution of direct reciprocity.
Okay, great. Thanks everyone for the invitation. I'm really glad to be here and have a conversation with so many bright and extremely interesting people. Is the volume good? Okay. Okay, so just to start to give some background, from a biological perspective, cooperation is particularly interesting. Because a trait is selected to the extent that it produces a competitive advantage with respect to its competitors, there's a certain, you might say, Darwinian obviousness to traits that directly facilitate competition between individuals. On the other hand, traits like cooperation, generosity, or altruism are all defined as behaviors that are designed for conferring benefits on others. And this initially presents an evolutionary puzzle. How can behaviors like helping others to achieve their goals, sacrificing your good for the good of others, survive the filter of natural selection such that we see them in populations today? The solution that researchers quickly realized was that cooperative traits must also yield competitive advantage. The difference, though, is that this advantage is not with respect to the target of the behavior, like it was with competitive traits, but with respect to non-cooperative individuals who aren't able to achieve the benefits that cooperative individuals are able to achieve. Aside from theories like kin selection or inclusive fitness theory, a family of theories that I like to call social exchange has been extremely successful in explaining a diversity of cooperative behaviors across species. Built on foundational theories like direct reciprocity and reciprocal altruism, social exchange describes a set of mechanisms for profitably extracting gains in trade through ongoing cooperative relationships with others. Whenever two individuals have goods or services that are more valuable to each other than they are to themselves, then there's the possibility for mutual gains in trade. However, upon upholding your end of the bargain, there's no guarantee that your partner will do the same. Indiscriminately investing in such a relationship would not yield a selective advantage with respect to the trait's competitors, and therefore would not survive the filter of natural selection. That's why a necessary component of any adaptation or set of mechanisms for engaging in social exchange has to be the ability to selectively discriminate between individuals with this disposition and individuals, and direct your resources towards individuals who would be profitable cooperation partners.
And Max, are you going to exclude group selection models then?
Let me get to that in just a second. Okay, so to summarize a lot of literature, social exchange theory has been extremely successful in explaining data across the range of species from humans to bacteria. In humans in particular, social exchange mechanisms have been observed in human reasoning, motivational systems, mechanisms of social attention and memory, and in their dysfunction playing a role in several psychiatric disorders such as psychopathy and specific brain damage. And this evidence has come in from a variety of sources, including behavioral measures, neuroimaging, cross-cultural data from existing hunter-gatherers, etc. However, researchers rapidly began to observe patterns of human behavior that seemed similar to what social exchange was able to predict, but seemed to fall outside the realm of what social exchange could predict. For example, one of the most highly cited cases you might think of as generalized generosity. So while it's the case that as humans we're able to achieve substantial gains in trade in ongoing cooperative relationships, we also seem to invest a substantial amount of goodwill and generosity into one-off encounters with anonymous others from whom we're unlikely to ever recoup such investment. So, what's going on with this guy? Why did he give this gift? In light of these apparently discrepant phenomena, over the past few decades, some researchers have begun to propose alternative models in an attempt to explain them. While the exact mechanics differ, for example, between strong reciprocity models and gene culture coevolution models, the underlying mechanics are generally the same and fall into a category what I like to describe as group norm maintenance. To give you an idea of how this works, the idea is that if you have a group of individuals that differentially uphold these particular social norms, they should be more successful in competition with other groups that are less favorably disposed. And this could be by out-reproducing that group. It could be by directly planting the norm for these cooperative behaviors into the minds of the other group's members, or through higher success at intergroup warfare.
I have a question.
Yeah.
But why would those norms take root in these other people? That seems to be the question to be asked.
That is definitely an important question to be answered. But for the sake of this talk, I will proceed with the assumption that it's a valid, that group norm maintenance is a valid theory with which to against which you can test. But we can talk about other problems with group norm maintenance. In case this isn't an area of research that you follow, there's been a storm of controversy about which of these theories actually accounts for these pockets of cooperative behavior, and people are pretty agitated about it. There's been publications back and forth in top journals, full-length books, hundreds and hundreds of pieces of scholarship, and considerable effort and research investment. Yet, despite all this scholarly work, the literature remains to be vexed. And the underlying debate has yet to be resolved. The argument that I'm making here is that this is due to a vital question which is yet to be substantially addressed, despite the scholarship. And the question is this. If it's the case that social exchange can actually select for these discrepant phenomena, or presumably discrepant phenomena, then the major evidentiary basis that group norm maintenance is derived on disappears. And so if you can actually settle this question, you can, at least in one part, settle the debate between these two theories. Okay, so let's get a little bit more specific. As I talked about previously, it's commonly objected that certain human cooperative traits can't evolve via social exchange. For example, the most commonly discussed example is the case of one-shot anonymous cooperation. In the real world, people do things all the time, like leave tips in restaurants when traveling in foreign places that they never plan to return to. They leave money in exchange for goods in honesty boxes, even though no one's looking. They make donations to charity, even such that the circumstances is structured so that the donor and the recipient remain anonymous with respect to each other. These are situations where it's unclear exactly how one's investment could ever be recouped. And the question is, can such behavior as one-shot cooperation evolve via a selective dynamic of social exchange? Okay. Work in this domain typically considers the game theoretic model of the prisoner's dilemma. Just to run through it briefly, not that I would need to for this audience, but just to make sure we're all on the same page. In the one-shot case, two players, A and B, each have the choice to either cooperate or defect on the other. In the one-shot case, we're going to interact once and only once, and here, each individual faces the temptation to defect. Because I can always do better by defecting on you than cooperating with you, the rational actor should always defect, and mutual defection is the expected outcome. In the repeated case, much of the situation is identical. Even though we might have a chance of seeing each other more than once, because we should expect people to be conditional cooperators, if either of us defects on the other should shut down cooperation in the face of that. However, if both of us cooperate and we see each other more than once, we have the chance of accruing a long string of mutual gains in trade that can add up to be quite substantial. So substantial that they can outweigh the temptation of defection, such that cooperation becomes the rational outcome and mutual cooperation the expected outcome. Okay, so From this kind of analysis, researchers have commonly asserted that while cooperative investments in repeated circumstances is rational, any observed donation in one-shot anonymous conditions is wasted effort for the donor. Because of that, the observation that people sometimes seem to intentionally cooperate in one-shot cases cannot be attributed to a psychology designed for social exchange. The problem is that this inference contains a hidden assumption which is seldom articulated. For this to be the case, the details of the situation have to be perfectly perceptible from the perspective of the organism. In other words, the individuals have to have perfect knowledge about what the future holds for the two individuals. The problem with this assumption is that it's almost always impossible to meet. As situations naturally occur, they don't come in either one-shot or repeated flavors. You don't know that until the interaction is terminated. No real mechanism can perfectly perceive the future, no matter how strong the cues are. If I think that we're in a one-shot interaction, no matter how strong the cues are to that effect, I can never be sure that that's the case unless you die on the spot. There's always, unless that happens, there's always a non-zero chance, maybe trivially small, but non-zero chance that we may encounter each other again.
Well, one of the problems is you may have a heart attack and maybe die or not die, depending on how you treated the person in what was alleged to be a one-shot interaction.
Right, exactly. That all goes to say that from the perspective of an actual organism actually having to make decisions, the question isn't why should I cooperate in a one-shot circumstance, but what do I do when there's uncertainty about what interaction I face? And all that's going to go into increasing the uncertainty of that decision. You'll almost never know this information with perfect certainty, which means that no matter what decision rule you use, you'll occasionally make mistakes. Let's look at the possible mistakes that an organism could make. In hindsight, the situation could actually have turned out to be repeated or one-shot, and you could either believe at the time that it's repeated or one-shot. If it's really repeated, and you believe that to be the case, you can cooperate and potentially earn the long-term gains in trade from cooperation. If you make a mistake and think that it's a one-shot interaction, you might be able to sucker your partner out of that one-time temptation for affection before she shuts down cooperation with you. In contrast, if the world really is one-shot and you correctly perceive that to be the case, you can succeed in holding on to the benefit. Whereas if you make the mistake, you might squander a one-off instance of cooperative investment before shutting down cooperation with your partner. Okay. A quick subtraction reveals that this is going to be the far more costly error to make, especially in a long-lived species like human that has a chance for a very long history of interaction when interactions are repeated. Okay. So the question that I want to ask is, in an uncertain ecology like the real world necessarily is, can one-shot cooperation evolve? Let's test it. To answer this question, I constructed a computer simulation of a population of agents. These agents were randomly paired into dyads, and dyads were assigned to play either a one-shot prisoner's dilemma or a repeated prisoner's dilemma. While I colored these agents like this for you, the agents didn't have access to this kind of perfect information. In real life, we might use cues like if we both speak the same language or we have the same kind of proclivities and interests to kind of infer what's the likelihood that we might or might not see each other again. To simplify the situation, I boiled that all down to a single value cue summary that was probabilistically associated with likelihood of interaction. This was modeled as just two overlapping normal distributions, one associated with each type of interaction. Agents assigned to play a one-shot prisoner's dilemma each drew cue values from the one-shot distribution. Agents assigned to play a repeated prisoner's dilemma each drew cues from the repeated distribution.
I'm sorry, what is it that they're drawing?
It's a cue value. So basically just a number from this distribution. You could think of it.
What does the number mean?
It's just a number that happens to be probabilistically associated with their interaction type.
And if it's larger, then you're more likely to be repeated. If it's smaller,
exactly. In our operationalization, it was centered on 0. So if it was positive, the more positive it was, the more it tended to be associated with repeated distribution. The more negative, the more the one-shot distribution.
Okay.
And that's all it was, just a number that was probabilistically associated with interaction type.
Did the players understand the relationship between the number and the probability?
To a certain extent. So let's get into that. So instead of seeing perfect information like this, the agent saw something more like this. There was random assignment of Q values to an interaction, to agents. And to see how the decision rule process proceeded, let's go down to a single dyad. So in this first simulation, let's imagine that you're this player. You observe that your partner has the following Q value. In this simulation, we want to assume as little as possible about the underlying psychology, just to make sure that we're not imparting something into the simulation that's going to be carrying our results. That's some unnecessary assumption. So in this case, we used a decision rule that was as minimally that was as minimally specific as possible. So all these agents did was they had a single gene, a single genetic regulatory variable that functioned as a decision threshold. You can think of that as a standard of evidence that they had, from which they were required to believe that the interaction was repeated. So if I observe a Q threshold, a Q value that's doesn't exceed my Q summary. Sorry, if I observe a Q summary that exceeds my threshold, I believe the interaction is repeated, and I therefore cooperate. It's just a behavioral trigger that triggers cooperation.
And Q summary is my signal and my partner signal?
Just the partner signal.
So you observe some information about your partner. You observe your own information or not? You don't observe your own information?
No.
Okay.
So we just want these agents to have at least a little bit of a cue of what kind of interaction they face.
Okay.
And a very minimal psychology with which to deal with that information.
How is different that of observing the signal about the state of the world? Like you're observing a signal about your partner, it's not really different.
You can think of it that way. Given that, so it's functionally equivalent to the dyad having a Q value assigned to it. It's just that the Q value is observed between the two partners can vary.
But you did this, it sounds like the way you proceeded this is because people think that there are things like language, idioms, which could be person-specific cues of chance of future reciprocations.
Right. When I'm actually experiencing the world and I'm experiencing potential partners, I need someone, I'm using information about them to adjust my expected probability of seeing them again.
But
Is the idea.
So there's this issue. So I see a Q value that indicates the probability or something about the probability that you assess to this being a repeated game. But I mean, I know that you're getting the same Q, getting an independent Q value about me, and that actually is what is an indication of how you actually perceive the repeated nature of the game, because it takes two to repeat, basically. It takes two to play cooperatively. So everyone, the structure here is common knowledge. I mean, everyone knows that these things are drawn from these distributions. And I mean, what's the information that a player has? When I see your Q value, and I know that you know that both of our Q values are taken from these distributions?
In some senses, no, and in some senses, yes. So operationally, agents have one gene and this simple decision threshold rule. If the Q value exceeded the threshold, cooperate. If the Q value doesn't exceed the threshold,
And players know that's the
you got that this is agent-based model?
what?
Agent-based model?
So what?
Oh, okay. I just, with your language, I thought maybe you thought it was human subjects.
Oh.
So you could think of this as they know things and then they're believing things about the world, or you could just think of it as they are sensitive to information and that triggers a behavior. This model is agnostic to exactly how that's operationalized.
I see. So in this case, so your behavior is only a function of the trigger of the other player's type signal that you get.
The other player's signal, yeah, and your genetic threshold. And the question is,
And that's given to you to start with.
yes.
Okay.
Okay. So let
That's
me get
good
into
with
that. So
agent,
just
okay.
as an example, so okay. So if this player, if you had a threshold here, their Q value would exceed your threshold, therefore you believe that they were repeated and would cooperate.
So your genetic threshold is a statement about the other player's signal?
It's a statement of your standard of evidence for evaluating
The other
player's
player,
signal.
okay.
And so the predictions that the theories make are as follows. If some form of group selection is required for organisms to be designed to cooperate in one-shot circumstances, because there's no group selection operating in this experiment, in this simulation, thresholds should evolve to be what you might think of as incredulous, that they're in repeated situations, in order to prevent mistakenly investing cooperative investment in one-shot cases. However, if all that's required for this to evolve is direct reciprocity under uncertainty, then we should find that thresholds should evolve to be credulous. In other words, to prevent missing out on long-term beneficial exchanges. So just to give you a better, okay, yeah. Okay. I'm going to get a little bit into the mechanics in just one slide, so if you just bear with me for one slide. Just to talk about the parameter space that we explored in the simulation. Across runs, we varied the benefits at stake in any given round of the prisoner's dilemma, from just marginally higher than the cost of cooperation up to many times the cost of cooperation. We varied how long repeated interactions were when they occurred, so between just 2 rounds on average to 100 rounds on average. We varied the base rates of the 2 types of interactions, so whether one-shot interactions were relatively rare or one-shot interactions were relatively frequent. We also varied the informational ecology, so how hard of a discrimination task do you have when you're given this Q value? Is it the case that there's a lot of overlap between the distributions or not much overlap? Then you have an easy discrimination task. And then across this parameter space, around 3,000 runs, each time a population of 500 agents evolving over 10,000 generations. And so
you did that for each permutation of the...
Yeah. And so the data that I'm going to be showing you is as follows. So at the beginning of each generation, agents were started out with decision thresholds that maximize accuracy. So when base rates were equal, that means that their starting decision threshold was 0. That'll minimize mistakes.
Excuse me.
Yeah.
It may minimize mistakes, but it doesn't necessarily minimize loss, or in other words, maximize expected.
That's the point. Okay. So what I'm going to be graphing for you is the probability of believing that you're in a repeated interaction, given that you're actually in a one-shot interaction. In other words, this area of the curve. If it's the case, the group selection is required for this to evolve in, we should find that this value either maintains at the level that maximizes accuracy or decreases. If, however, direct reciprocity is sufficient, evolving under uncertainty, we should find that this probability
I'm
expands.
confused. Why is that little area under there, the probability that you believe you're in repeated, given that you're in one shot?
So if I have this threshold,
Oh, I see. You're using that.
this proportion
Okay. Okay.
of the time, yeah, okay?
Okay.
Okay. Yeah.
How do you evolve from one generation to the next?
So agents accrue fitness given their prisoner's dilemmas. That fitness is then probabilistically determines the next generation composition. Basically, it's a multinomial distribution that you sample from until you refill the next, where the intervals on the multinomial are fitness.
And fitness is payoff or fitness is accuracy?
Fitness is payoff. Okay. So before I get to the aggregate data, let me just show you the population, the evolutionary dynamics over several runs to show you how it evolves. So for these runs that I'm going to be showing you, the base rates of the 2 interaction types are equal, and the spread between the 2 distributions was 2 standard deviations, meaning that there was a 32% overlap between the distributions. So it was a moderately difficult discrimination test. On this graph, on the vertical axis, is the probability of believing you're in a repeated interaction when you're really in a one-shot interaction, and then how that evolves over generations 0 to 10,000. Okay? And here's 3 runs. What you're seeing is that when benefits of cooperation are relatively low, and repeat interactions when they occur are relatively short, agents do not evolve to believe they're in a repeated interaction when they're actually in a one-shot interaction. However, as soon as one of these variables is even marginally increased, so that interactions that are repeated are just 5 rounds long or 10 rounds long on average, the picture dramatically changes. And all of a sudden, agents evolve to believe they're in a repeated case 62% of the time if they're actually in one-shot interactions. Agents with this threshold successfully identify 98% of repeated interactions, but only 38% of one-shots. And therefore, they're cooperating 62% of the one-shots that they find themselves in. Okay. So here's the genetic regulatory variable over the entire parameter space, the final 500 generations averaged across the entire simulation. So it's the same horizontal or vertical axis with within round benefits here from large to small, and interaction length from small to large going back and down. Here you're seeing that when cooperation is not very beneficial because within round benefits are low and repeat interactions when they occur are relatively short, agents who believe they're in agents do not evolve to believe that they're in a repeated interaction when they're indeed in a one-shot interaction. However, as soon as either of these variables is eclipsed, agents evolve to reliably, the majority of the time, believe that they're in a one-shot repeated interaction when they're indeed in a one-shot interaction. Okay. So, given this data, there's a common objection that people have often expressed, and that's this doesn't actually map onto the human experience of what people are seeing in experimental games. So, humans, if you ask them, if you instruct them that they're in a one-shot circumstance, they often report believing you that they're in a one-shot circumstance, and yet they were cooperating anyway. And that's actually not the phenomenology of what I just described for you. These agents were actually forming mistaken beliefs. And so the assertion is that these data so far haven't explained the human data. What I would like to argue, though, is that natural selection doesn't require behavior to be consistent with belief. We can ask the question, well, let's allow these agents to form their beliefs rationally. Give them every tool in the toolkit to form rational beliefs, and then look at how natural selection causes them to behave, given those beliefs. Let's look, instead of looking at the formation of a belief, let's look at the implementation of a belief. In other words, how are rationally formed beliefs translated into adaptive behavior? Are you more cooperative than if that behavior was always consistent with the beliefs you formed? So, new set of simulations. Everything's the same except we're just changing the psychology that these agents have. So now, instead of having a single genetic threshold standard of evidence, these agents have a more elaborate psychology. So if you're this agent and you observe your partner has this Q value, what we did was we gave the agents innate knowledge of the informational ecology, the Q distributions, and the ability to perform Bayesian updating to arrive at maximally rational beliefs about the state of the world, or the state of their interaction, given the evidence they observe. Okay? The agent then, what we then did was allow natural selection to answer the question, how should you behave given that you formed that belief? So, once they formed that belief, the agents accessed a computational variable which regulated the probability of cooperation given that they formed that belief. So there was one variable regulating cooperation given a one-shot belief, and another regulating cooperation given a repeated belief. So this agent forms her belief, accesses the variable, and cooperates with a specified probability, for example, 10%. Okay. The question is, and then we put the variable, expose it to mutation and natural selection, allow it to evolve. If group selection is required for agents to evolve to cooperate even though they believe they're in one-shot interactions, because group selection is not present in this simulation, we should find that this variable, this gene does not evolve in. However, if the only requirement is a selective regime for direct reciprocity and requirement to make judgment under uncertainty, we should find that this gene can indeed evolve. Okay. So just like before, I'm going to first show you some sample simulation runs so you can see the evolutionary dynamics. This is from the exact same parameter space that I showed you before. equal base rates and median spread between the distributions. Just to give you an idea of what this means, an agent performing Bayesian updating on perfect information would only be making a 16% error. So 84% of the time, they're going to be correctly perceiving the kind of interaction happening. They're generally pretty accurate. Again, on the vertical axis is the level of the gene, the probability of cooperation given a one-shot belief, evolving over generational time. And here's those same 3 points. When benefits of cooperation are relatively low and interactions are relatively brief, agents who rationally believe that they're in one-shot interactions do not evolve to cooperate, given that belief. However, as soon as interactions are even marginally longer, repeat interactions, they're still in a one-shot interaction, but repeat interactions when they occur are marginally longer, all of a sudden agents evolve to cooperate around 95% of the time.
Even when they think that it's a one-shot game.
Even though they rationally perceive that the most likely thing is that they're in a one-shot game, and 84% of the time they're right. They still evolve to cooperate 95% of the time anyway. So here's those stabilized values for the full parameter space. Probability of cooperation given a one-shot belief, within or on benefit from high to low, and interaction length from low to high. Same pattern as before. When cooperation is not very beneficial, and when repeat interactions are brief when they occur, agents who rationally perceive that they're in a one-shot interaction do not evolve to cooperate anyway. However, as soon as the space is eclipsed, these agents evolve to dramatically cooperate given a one-shot belief at a rate that rapidly approaches 100% of the time.
I missed something, I think. What is the Bayesian prior you're updating on if your belief state is zero?
So the Bayesian prior is the base rates.
Is what?
The base rates. So you're
Base
given
rate?
the base rate of the two interaction types.
Where does that come from?
We just gave it to them.
So somehow it's a belief in nature. It's not my belief. It's I have no conscious awareness of this belief. So you're updating.
I mean,
See, usually, the posterior is zero if the progress. If this probability is a priori zero, then there's nothing to update on.
but the prior is never zero. The prior is the base rate of the interaction.
Okay, so it's, and that base rate is somehow different than belief.
So they're given the base rate. So for example, if 10% of interactions are one-shot, my base rate expectation, my prior probability is that 10% there's a 10% chance that I'm going to be in a one-shot circumstance and a 90% chance that I'm in a repeater circumstance.
Genetic information.
And that's independent of every generation, that's independent, right?
The ecology was fixed in a simulation run.
So that from generation 1 to generation 2, it's still the 10%, 90%.
Exactly.
And then I get a signal, and then I play a mixed strategy that's optimal to payoffs given that signal, and we watch that mixed strategy evolve.
You play a mixed strategy that will evolve with the optimal payouts.
That's kind of
Starts out optimal to consistency.
Well, you see what happened, and then if that was positive, then you put more weight on that probability of playing one way. If it turns out negative, you put less weight on it. I don't know what your updating rule is, your updating heuristic is. But
You're updating based on both the signal and actual play, right?
Say that again.
Are you updating both on the signal you receive, which is somehow related? We were never clear about how the signal enters into Bayesian updating.
Okay.
But
so-
also on actual play, because the actual play of the other player is presumably not affected by the signal. Well, it is, but it's in a strange way because he's basing his decision on your signal,
Right.
which you don't have. So his behavior may be very inconsistent with the signal.
So decisions happen simultaneously and were not updated.
And are not updated.
No. So I don't take your behavior as evidence of the kind of interaction we're in.
Okay.
So, I still have a question.
Yeah.
I mean, it's not surprising for me, right? I mean, if you think about setting up this kind of simulation or model, or you probably could even solve it, using game theory. This is not a very complicated simulation to begin with. But so if you set up the model that there is a slight possibility of a mistake, or there is a slight chance that this might be a repeated interaction, and then reward for that repeated interaction is so much higher than the one shot, then you're going to get a really high rate of cooperation. But then
that's both the insight and the result.
Yeah. So this is totally common sense. But again, that doesn't answer the question about
common sense, but not universal common sense.
Okay.
No, but there is the literature on sort of epsilon chance of facing certain types of players leads people to pool in that behavior and that sort of thing. So there's literature on reputation building, and the game theory literature is seems like it's very much that type of thing. I mean, it's
and so then I don't see that as surprising. Again, maybe in anthropology or people are not convinced about that, but still, it's about one-shot interactions. Like most of the examples that you gave, charity giving, tipping. I mean, those are really one-shot. There is.
How do you know that?
Me giving to charity when they cannot identify me at all. I mean, and some people donating,
How do you
completely
know?
Anonymous.
You may have a heart attack right after you
There's
go
always
past
a chance of
that.
informational leakage. There's always a chance that plans will change. There's always a chance that there's a mistake somewhere.
But that's
along
not
the
going to be
line.
100 rounds of interaction. That's my point. That you can go up to 2, probably, maybe 5.
But it's not that all around. So this is not a world where all interactions are that long. It's only when you have a repeated interaction, it isn't that indeed on average that long.
But those
there's plenty of one-shot
should give you
interactions.
so much higher benefits. That's the whole point about this picture, is that the benefits from this continuing interaction should be so much higher to actually get that, cooperation going. So, and my argument is that's not the case. That's not the
we
case.
don't have high gains in
He's
trade.
taking an evolutionary, long-term view here.
I'm
I
fine with
think,
that.
I think that what is.
So
What you're arguing is we live in the lower right.
We are, with those examples that were given in the beginning, I think in a lot of we are in this first quadrant.
No, this is not saying that every person you meet, you only have a 2 rounds on average. It's saying for the repeat interactions that you have, they're on average that long. These were cases, we evolved these genes in cases where 90% of the interactions were one-shot, and the 10% of interactions where they occurred were this long.
I mean, you could also get
Even
this.
despite those extreme base rates, we still get this behavior evolving.
You could have in this situation, rather than having the number of interactions, varying that, you could think of the possibility of small numbers of interactions, but much more valuable interactions arising. So, to give the example of tipping, you're on some interstate highway. Why should you tip if you're not going to go back there? But if you go out the door and you find out your car won't start, maybe you'll want to walk back in. And the stakes of not having your car start and not being able to get help or something like that vis-a-vis the tip is quite large. So you have this small probability of a very large stake interaction as well. It sort of leads to a similar situation, I think.
So I'm not meaning for this to be a veridical model of anything.
Yeah.
Just as a simplification for the dynamic to be minimal assumptions, but
The result is very
basically.
possible. I mean, it's not counterintuitive or anything. That's why.
The goal is to change the intuitions, because a lot of people found this without the data to be counterintuitive. So I'm going to move on to, just in case people were interested, we also have an analytic model. But it's basically showing, it's going to be convergent evidence, and I don't know if the questions people have want to be answered before and are specific to the simulations, or if they want to wait until after.
But I can do before.
It wasn't clear to me, do the agents know how long they'll be repeating these games? do they have? What kind of strategies do they follow? Right. So just because if they know that rationally there could be backward induction, or
there's
trigger strategy won't necessarily work thoroughly enough.
There's no rational backwards induction decision making. If their strategy specifies to cooperate, they play tit for tat. If their strategy specifies to defect, they play always defect.
The only learning that's going on is the reinforcement that's going on from one period to whatever you want to call it, shifting these parameters, these sort of thresholds.
Yeah.
There is some theoretical game theory that has, like, for example, in global games, where even just by relaxing the idea of common knowledge of the payments, that it's in some way relaxing with your queue thing, you don't need even to have repeated interaction to get.
Yep.
Yeah. So
there's a lot of reasons why cooperative behavior may not be all that surprising in a species where mutual gains in trade can be quite substantial. That's the take-home message. It's not, it may be appreciated by many people, but it's certainly not universally appreciated. Yeah.
So what I'm wondering about here is when you, for a lot of us in the room, this is not really all that surprising, as you're probably getting the sense it is for various reasons. What I wonder about here is the sort of the fixed ecology assumption, and that the people, the genes, you might have two genes, and one of the genes might control how often you switch partners, right? And so in a teaching world, you can have sort of vagabonds, right? Sort of, or con artists, if you like. Guys who go around engaging in one round, defect, and then move on to another sucker, right? And it seems to me that although this is all, this makes sense to me and none of it's all that surprising, adding a gene like that probably makes things more complicated. And probably allowing the repeated nature of the game to be a choice. Allows the population to be invaded by jerks. Have you guys gone down that route to try to think about that, or things related to it?
We have, not in the dyadic case, but in the group case, exclusion versus labor recruitment, for example. But the basic impetus for the simulation was by no means to have a veridical or realistic model. We wanted it to be such that the assumptions were minimal but valid in the ecology. So we want to say, look, the real world contains uncertainty and always did. You could never know this information, or the cases where you could know this information with perfect certainty is vanishingly small. Parameter space, we're not making point predictions about behavior. We're just saying that as long as there's these kinds of dynamics, we didn't want the simulation to be so complicated that there was non-monotonic effects such that it required specific combinations of parameters. We're really just getting two basins of attraction. When the long-run benefits of cooperation are low, it doesn't evolve in. When long-run benefits of cooperation are high, it evolves in. That simplistic structure allows you to say, look, it doesn't really matter what the particular instantiation was. And we instantiated this in two completely different psychologies across big regions of parameter space, with behavioral instantiation errors, which I didn't tell you, and without behavioral instantiation errors, and a couple of different specific cooperation strategies. And no matter what, the results were identical. It seems to be a reliable selection pressure that could reasonably be assumed to have shaped human psychology. We're not saying that the actual human psychology looks like this.
As I said, this is a kind of variant of axle-arousal competition. I mean, you've got in that model, in that environment, your agents are stuck with, I don't recall what the duration is, but repeated games right from the outset. And
300 years.
300, okay. And tit for tat, does remarkably well, and can evolve to beat out almost any other population or any other set of characteristics. What you've done is basically, isn't it basically, you've done sort of axelrod here with a certain probability that that suddenly they're going to find it isn't repeated after all. They get sort of, and as you increase the until you get to an extremely high probability of it being one shot, or until the repetitions get very few, basically tit for tat keeps winning, evolving. That's sort of my read on part of basically what's happening here. Tit for tat works really well, even unless there's almost no repetition, or unless the payoff is really small. Payoff to cooperation is really small. Once they've evolved to all being these cooperators and they're all making potential, what happens? Can it still not be invaded?
Well, so because we're looking at continuous strategies, invasion is a different kind of question.
So you really don't have, I mean, you've got people evolving toward concluding that we should always pretend, we should always act as though we're in repeated games.
Yep.
In fact, it almost never happens. In that setting, it would seem like somebody who takes a different strategy and always defects would do really well. Is that in fact what would happen? No, they just don't do well.
Across all of the simulation runs, mutation was a constant pressure.
Okay.
Mutation was constantly able to drive the genetic probability down if that was selected for. It just wasn't in this parameter space.
Tit for tat's just really hard to beat, right? I mean, even if you have two types and you're just a defector, then sometimes you're going to be running tit for tat and you'll get like a little bonus. And sometimes you'll be running into other people like you and you get nothing. Yeah. And if you're tit for tat, sometimes you'll be running into other people like you.
What about tit for tat for cheat in the last period?
They didn't know how many periods.
Oh.
Probability of moving on to the next round was probabilistic. Okay, just to show it a different way, in case people were interested in, we also modeled it analytically, this last model of Bayesian updating. The way that we approached the question was, what's the best response you can take given such an ecology? The terms we needed to model this kind of ecology were as follows. So if we let theta one-shot be the probability that an agent believes they're in a one-shot interaction, given that they're actually in a one-shot interaction. This is just so that we don't actually have to analytically model Bayesian updating. Let theta r be the probability that you believe you're in a one-shot when it's truly repeated. Alpha I is the probability that agent I cooperates, given that he believes he's in a one-shot. So that's that gene. Beta I is the probability for the repeated belief. P is the proportion of interactions that are actually one-shot, so the base rate of one-shot interactions. B is the within-run benefits of cooperation, C is the cost, and W is the probability that an interaction continues. In order to figure out the fitness effects of the various decisions, we have to look at all of the conditional probabilities. So just to give you an idea of what they all are, a P proportion of the time that I have one shot, a theta OS proportion of that time, agent 1 believes it's one shot, a theta OS proportion of that time, agent 2 also believes it's one shot, an alpha 1, alpha 2 proportion of that time, we both cooperate, it's one shot, so we get B minus C, etc. Just I cooperate, I pay the cost, just you cooperate, you get the benefit. Or sorry, just you cooperate, I get the benefit, neither of us cooperate, I get 0. Yeah, so for each of the possibilities, across all of the combinations, that gives us a big, long fitness function. If we derive this with respect to alpha 1, that gives us the optimal response, given that I believe I'm in a one-shot circumstance. with a little bit of algebraic reorganization, that gives us this equation. This equation basically has two terms. This first term has two elements. The first is the long-term benefits of cooperation, devalued by a slightly different formula. And then a bunch of probabilities that are all going to be strictly between 0 and 1, but under realistic assumptions are going to be relatively high. And then you subtract from that the cost of being a sucker, devalued by some other probabilities. And the way to interpret this is, whenever this term is larger than this term, the optimal response is to always cooperate. You believe you're in a one-shot circumstance. And whenever it's less, always defect when you believe you're in a one-shot circumstance. And if you plug through for realistic assumptions of benefits and costs, you get the convergent result from the previous study, or from the simulation studies, that this term is, for that parameter space, going to be larger than this term. So, to conclude, and I'm happy to answer questions, obviously, I think that from these results we can say that cooperation in one-shot encounters may in fact be a reliable byproduct of design for social exchange and not some other selective dynamic. These results required really minimal assumptions about the ecology, and I would argue actually more realistic assumptions about the ecology than the assumption of perfect knowledge. These results are robust to many conditions. We modeled the psychology in completely different ways. We included instantiation errors. We looked at big ranges of parameter space. The results don't seem to be highly contextual dependent to any of those changes. They seem to be just one big effect, depending on the benefits. As such, I argue that social exchange is a viable model of behavior and that it's unnecessary to move to group norm maintenance to explain it. It's important, though, to understand that I'm not making the claim that all of our social behavior is a product of social exchange selection pressures. That's certainly not the case, and it's not the claim I'm making. However, group norm maintenance went astray because it forgot about the ecology. Real ecologies are full of uncertainty. That's just a feature of the natural world. But if you forget about this, and you see people cooperating with strangers, that might seem strange. Whereas if you remember what the natural ecology is, it all of a sudden seems less strange. To move this debate forward, I argue, requires considering three pieces of evidence simultaneously, or three pieces of reasoning simultaneously. Not only do we need to consider utility and fitness dynamics, but we need to think about structural regularities of ecologies, specifically ancestral ecologies, but also realistic psychologies that can take advantage of those regularities. And that's really the only way to get a clear picture of what's going on with human nature. I'd like to thank my co-authors, and thank you for your kind attention.
So I want to follow up on what Roman asked. I don't know if I'm thinking about this clearly or not. So I guess there's one way to think about it is, were there identifiable one-shot encounters in whatever you want to call it, the ancestral environment? And then if there were, how do those line up with the situations that we see today that we may believe are one-shot encounters? Is that a fair way to think about it?
Yes. So, I mean, there's several questions embedded in that. So let me just maybe answer a few of them, and if I didn't get the one that you had in mind, let me know.
Can I just clarify one point? So again, the landscape as we see it today is that we observe generosity in what we know today are one-shot interactions. And in the group selection models, that works okay, as long as those people are in that evolutionary relevant group. If there's no existing individually selected framework that says that those behaviors are adaptive. Is that the landscape that you set in the beginning?
I would argue that the situations are, from the organism's perspective, reliably one-shot, or uniformly one-shot.
I'm sorry, which situations? So yeah, the puzzle is, you're nice to someone who we know is a one-shot today. Where do they come from? There are models that explain that as an outcome of group selection, and there are not models that explain that as the adaptive outcome of individual selection. Is that correct, prior to yours?
There's been theoretic discussions that are very similar to this. I think this is the first analytic model or simulation model that shows it to be the case. we know for a fact, I mean, just like experimenters, we know as much as someone can know whether an interaction that these agents had was one-shot or repeated. The agents are like subjects. They have probabilistic knowledge. They can't be certain.
But are you saying there are no situations in the model world that actually are one-shot with certainty?
I wouldn't say no. I would say vanishingly rare. That you can know at the time that you're making your decision.
I see.
Because the question isn't in hindsight, was it one shot?
Yes.
But when I'm interacting with you now, do I know for a fact that it's going to be one shot? Can I predict the future with such certainty that I can say you will never influence my life again? Or even have the chance to?
Right.
The person you cut off on the freeway on the way to the job interview might just be your interviewer. I mean, there's so much we don't know about the world. The world is a hugely complicated causal structure with a lot of chance and uncertainty, and weird things happen. And when there's at least a little bit of uncertainty, I mean, we didn't have to put much uncertainty in this model. So we, just to give some bite to that, we put all the data into a big OLS regression framework to look for the effects of the various parameters. There was very little effect of difficulty discrimination. So even when the distributions were separated by 3 standard deviations, and there was only like 2% overlap between the distributions, agents still evolved to have levels of cooperation very similar to what we saw.
Did you vary B minus C?
Yes.
You probably would need higher B minus C for those 2%.
Not much. There's
I mean, it's not much.
There's a tight little corner of parameter space when one-shots are really common, so like 90%, and discrimination is really easy, and agents are making 5% behavioral instantiation errors, meaning that 5% of the time they intend to cooperate, they actually defect, and they're actually playing grim in this case, so that immediately shuts down cooperation with the dyad. In that case, it's a smaller space that allows for the evolution of cooperation in one-shot circumstances. Except for that one little pocket of parameter space, it's pretty much the same story.
But so you say that there is virtually no chance, there are no instances where you don't meet, sorry, I'm putting this wrong. I just think about the way that most of the charity giving experiments are run in the lab. Okay, let's say you go to the extreme when subjects are given $20, they sign out their consent forms. It's my $20, it's all $1 bills. There is 25 subjects in the lab. And then just anonymously, they pass hat, and everybody contributes whatever they want from this into this hat. And then at the end, the experimenter gets the hat and sends us off to a charity that was, let's say, Red Cross. There is complete anonymity. There is no way, your name is never there. There's no way you're going to interact with anyone from that charity. I mean, the probability is 0. Okay, explain to me where it is. Where does it come?
So
how do you explain why?
From a subject's perspective, I have a reasonable suspicion that the experimenter might make a mistake in their data coding. I may have a reasonable suspicion that I might bump into someone and they might know something about me. I may have a reasonable suspicion that maybe if we were filling out pieces of information or however we were conveying this, that someone got a peek at something. There's a million ways in which information can be leaked, and I can't be certain that none of them held.
Okay, so then you ask subjects. There are 20 different things. Which one? Why did you give? Did you give because you thought that somebody is going to follow you, and actually will figure out what you did? Or do you think that this was normal, usually accepted norm for people to donate, some part of the income? And I don't know what the outcome would be, but I'm sure it would be something else.
Right. So the second simulation result, these agents had rationally accurate beliefs. They believed they were in a one-shot circumstance. They were sure of that. I mean, that's the belief that they were holding. And as far as these agents were concerned, that's the way that things were. But natural selection caused them to cooperate nonetheless. They had a motivational desire to cooperate despite the fact that they had a rationally accurate belief that they were in a one-shot circumstance. And that's because of the selection pressure, because nothing else was in effect in the simulation. we're not committing to any particular instantiation of the mechanism. We're just saying this selection pressure is broadly applicable.
Okay.
So again, Max, just to repeat the same question, it seems like, I don't know if you've taken a stand, but it seems like there are two possible stands you could take. One is that there are almost no knowably one-shot encounters in the modern world, and that's why the behavior is optimal in any environment. The other is that there's been some significant shift between the ancestral environment and today, and there were even far fewer of them in the ancestral environment, and therefore the appropriate level of subconscious or non-cognitive, non-explicit cognitive knowledge assumption that's built into our brains is to assume far more likely either anonymity, lack of anonymity, or repeat interaction, right? And either one works, right? It doesn't matter whether it's the same person or not. It's just that the information gets out to anybody. And so
Should you want me to take a stand?
well, do you have one? I mean, again, the way you answered Roman's question was, even in the modern world, there could be a camera in there, you know anything about it, always pays to be a little bit nice, you know? But that seems quite different from saying your brain is built to reflect the ancestral environment. And I can quote John and leave other pictures up there. Nice to see you.
I like Perry's argument because it kind of gets at my question. If you think about the societies, 1,000 years ago, I mean, they were really not anonymous, right? I mean, it was a community, and that probably built the genes, that are, evolved eventually, and that's how we behave today. And that goes back, that there was really those probabilities of anonymous interactions were very, very, very low. While now, maybe they're much higher, but we still carry that.
So I'm curious. I mean, there's the discussion of this issue of how people might behave differently under scrutiny versus not under scrutiny. And if you tried to tap, the scrutiny issue would come in. People would know they're being observed, being non-cooperative or something. It seems very hard for me, hard to tell what is the sort of the scrutiny issue in a lab type of situation versus the evolutionary, wanting to cooperate or something like this.
So, I mean, there's a couple of different questions on the table, but let me just try to answer them together. My general premise is that the mind is composed of many mechanisms that are there because of a history of natural selection, that you're never responding with just one mechanism, but it's the sum of your mechanisms that are outputting your behavior. It's likely, I think, that there are mechanisms, so natural selection is a filter, and the genes that survive the filter are the ones that are present. It's not backwards looking at selection pressures that causes, or it's not forward looking at possible current situations that cause mechanisms to have the shape they do. That's not to say that we don't have mechanisms for making use of immediately accessible information. So I think that there's certainly both kinds of mechanisms at play. That said, I think there's lots of reasons to expect people to cooperate in situations that really look like one-shot circumstances, such that it should be in no way surprising that they do, and should cause no one to jump to a group selection conclusion without actual design evidence that that's what the behavior is for. I mean, it seems like people are happy with this assumption, that they think it's obvious. We're willing to and able to come up with alternatives that would cause the same thing. So the one conclusion we should make is that the behavior is really not all that surprising on lots of different theories. And so there's really no impetus to move to an alternative selective model. And I'm happy with that conclusion.
Do you think you can account for species differences in the extent of cooperation, especially with some species is very narrow and strong, but it's not general?
I think this model gives some insight into that question. So for many species, the possible gains in trade are not general, not very large, or either not general or not very large. They either exchange specific things, like one thing for one thing, or what they exchange, there's just really not that much that they can do for each other. And if this were the only selective dynamic that were creating cooperation, you would therefore expect that they wouldn't have mechanisms like humans do for just default generosity towards others, even without being sure they were going to be in a beneficial cooperative interaction.
Now, the existence of this base rate, non-zero base rate in itself, mutation. Okay. Where does that come from? See, it doesn't need to have anything to do with beliefs.
Yeah.
Because it's totally below.
Why we have that base rate as our prior?
Yeah.
Yes. I would suggest that it would be advantageous to have it. We have another simulation suggesting at least one possible mechanism where that base rate comes from. If you have a world which is larger than you can circumnavigate in a reasonable length of time, there's going to be correlation between individuals' locations from time. People who start out close together are going to stay close together. So people you're going to have a higher chance of re-encountering someone that you've encountered than someone that you haven't encountered. So in a kind of sticky world, or a world where you're traveling by foot, odds of re-encounter are going to be non-zero. And we've explored that. There's parameter estimates for migration rates for all described hunter-gatherers, and we've run the simulation for just random walking for that entire parameter space, and across that entire parameter space, encounter predicts re-encounter at a non-zero rate.
Well, let me ask you, related to that, I propose this alternative that it may not be the number of times that you encounter each other, but the actual gains from cooperating when you do encounter. And you look around in the human species, for instance, my Dutch colleagues tell me that the reason that the Netherlands is a welfare state is because in the old days you had basically a weakest link public good where you had to maintain the dikes, and if someone didn't maintain the dike, then everyone suffered for it. So there was enormous gains from cooperation and enormous gains from not having free riders who didn't maintain their part of the dike, versus everyone would suffer from that, and because of that they're much more willing to redistribute income, say, and things like that. Now that's an anecdote, but it does indicate that there, in that particular case, you really had enormous gains from cooperation because you really could not succeed on sort of an individualistic basis keeping the water back. Now this must be true, across species. It must be true, different human populations where this type of public good provision was very, very important, whereas other situations it wasn't that important necessarily. And presumably there are variations based on that, not simply the number of repetitions, how often you're going to run into people, but what's at stake when you actually do have to interact.
Yeah. This literature is under a current state of kind of surprising controversy. But my reading of the pattern of data from other species is that cooperation precisely emerges in cases where there's extreme benefits. If the alternatives that I'm facing are doing one thing that can increase my chances of reproduction, hardly anything at all, or actually give me a 50% chance of having a copy of my gene in a relative, that's a very asymmetric cost structure. I can't say that I follow all the math of the current debate, but it seems to me to accurately fit, that what you're describing accurately fits the animal literature just fine.
I find myself in agreement with the analytical side of this. I think several of us think it's kind of intuitive. That's maybe being unfair to you, but one of the problems I'm having is that, let's go back to the central, the prime example, which is tipping. Only Americans would, I think, jump to the conclusion that this is really important. Go anywhere else, and tipping is about, an order of magnitude smaller. Americans run around the rest of the world saying, gee, how many dollars should I tip? And someone said, what do you mean? You mean how many pfennigs you should tip, right? And this highlights one thing, and then I'm going to get to the other thing. One is that this is very much a social norm which in this particular case happens to be very kind of special to the U.S. More generally, it also highlights that the question I'm always asking myself when I'm deciding how much to tip is, what are the other people going to say around me? There's a certain concern that the cab driver or the waitress is going to scream at me at the way out or not fix my car. But frankly, what I'm really worried about is what my wife or my girlfriend or somebody else. That's the repeated interaction that I'm worried about, and I don't have to assign low probability to that. It's just maybe if I write the tip, close it down, and then hand it over, I can minimize the chance that my wife's going to know that I've been a jerk. But
So you're a jerk when you go out alone, huh?
No, because I'm never sure I'm really alone. So maybe I'm the jerk in the room here and everybody else, but I'm operating as though there is repeated interaction, but it's coming through a group, not the person I'm actually apparently interacting with, and that in turn, the costs are going to be determined by various norms that I certainly can't explain this way when it comes to tipping when you look at the U.S. versus Europe or Australia.
So,
do jerk experiences change your behavior, Larry?
Oh, dramatically.
Well, see, Europe, the tipping instinct is so strong
Heard it's robust.
that they put it in the salary to start with, and you don't have a choice based on the quality of service. So.
I mean, all I'm saying is if I thought that I wasn't expected to tip much, if I thought that my wife or my girlfriend or my friends would think nothing of me, if I tipped 5 cents, I'd probably be tipping 5 cents.
Okay. That's changing the prisoner dilemma payoff matrix, right?
Well, he chose the example, so you're kind of stuck with the example.
So what I would say is, A, these aren't point predictions. B, this is not saying this is the only mechanism ahead. This is just saying that even in the absence of reputational concerns, mating effort, costly signaling, whatever other selective dynamic you think might be going on, even in the absence of them, we still shouldn't expect people to always defect in that circumstance. That's all I'm saying.
But I think that this is a really nice and important question. So you have a lot of possibilities here. Norm is one. Group adherence is another one. Obviously, the probability that the interaction is not one shot is yet another one. If you're comfortable as a psychologist to do a kind of deception experiment, you can actually ask people what they believe at the end. Why did they behave in a certain way? Let's say in the prisoner's dilemma game. In our lab, when we tell students this is a one-shot interaction, they know this is a one-shot interaction. So the probability is...
That's not true.
You of all people.
That's not true.
So when you tell, if you don't tell them, they still have a fire.
But definitely people were surprised.
When they, when
they
you
were
surprised. That's true.
Let me run a thought experiment.
Here's a thought experiment. At the end of the experiment, you can actually disentangle what is really driving, what kind of beliefs people have, whether it's really one theory or the other. I mean, this is just...
Even as a psychologist, I'm not super concerned with what people do. I'm not necessarily committed to a model that that's the causative force in predicting their behavior, or at least all of their behaviors. Let me just give you a thought experiment as an example. We have mechanisms for mate attraction. Men are generally attracted to cues of youth and fertility, yet it's not the beliefs about youth and fertility or the likelihood of future reproduction or the number of babies that woman could potentially have in the future that are driving causatively our attractiveness ratings. I can tell you that because we have attraction responses to 2D images on paper. We have attraction responses to contracepting targets. Even though I might believe that my partner is on the pill and I'm using a condom, I still have a mating response. The mechanism isn't cognitively penetrable to the belief, and it can't even read out the design pressure that caused it to have the shape it has. I have no reason to think that any particular mechanism of the brain would satisfy both of those constraints.
I think also it's worthwhile pointing out that there's a lot of evidence from the past that when you ask people at the end of an experiment what did and did not affect their behavior, that they say there are things that did, that just, vice versa. That's an old theme in social psychology, so I'm not even sure you can rely on those kind of retrospective reports.
Well, it looks like you provided us good food for thought, and Mike, if you have one more thing to add?
Well, I was in, let me just get your reaction to things. I'm in Hong Kong. It's 1978, first time I've been there. There's 2 hotels where people are having their conference. The conference was in the other one. I'm in this. It's about a 10 or 15 minute cab drive. So I come out and cab comes up. As the guy comes up to me, he says, "Would you share a cabbie?" I said, "Sure." So we got in. We talked for about 10 or 15 minutes. The other hotel. I get out my side. He gets out his side. He says, "Cheerio." Well, I paid and tipped the cab. And I asked myself, would I do that? Would I repeat that if it happened again? Sure. Even if he had a British accent. Now, why is it?
Wasn't costly to you.
Well, it is.
I would say that
No, is it?
one particular
having them into-
instantiation that I think is likely of how this selection pressure might have played out in the design of human nature is that we have a motivational system that just wants to do that. That's as complicated as the system has to be to take advantage of the structural regularity of the environment. Just have a motivational system that likes to do that, wants to do that. And you'll get, under appropriate ecologies, an organism that has higher fitness than its alternatives. That's not to say that every single time it behaves, it'll be realizing its goal, that the mechanism will be realizing its goals. It's not to say that if the environment changes, the behavior will stay the correct adaptive choice, but that's the result of natural selection operating on traits. I think that one reasonable way it could happen is a motivational system that have that structure.
Sorry.
Okay, so we can continue these conversations in reception up there. Thanks, Max.